Let's pick up with the electron configurations of elements number 5 through 30. We've done the first 3. We've done both the full electron configuration and the abbreviated electron configurations. And so I'm going to actually go through and do primarily the full electron configurations, and every so often do an abbreviated one, but I may not do every single abbreviated one. You can sort of pick up from there based on the understanding of the core electrons and all that. I think it's more important to get a lot of practice with the full one and then pick a couple of the abbreviated electron configurations. So what we're really doing here, we'll be writing the element down, number of electrons, putting together the electron configuration. Remember, we're filling orbitals from the lowest energy to the highest energy based on this chart over here, right? So the 1s, the 2s, the 2p, the 3s, the 3p, 4s, 4p, etc. On up, we're filling from the bottom up, where each orbital can fit 2 electrons. Now, there are sets of orbitals where, for example, the p orbitals, anytime you have p orbitals, there are 3 that are of the same energy, right? If you have d orbitals, you're going to have 5 orbitals that are all the same energy. So that'll account for 3 orbitals account for 6 electrons for the p orbitals, and the 5 orbitals when you have d orbitals will account for 10 electrons. So let's go pick up with element number 5, which will be boron. So boron will have 5 electrons in it. So in its ground state, the first 2 electrons go into the 1s orbital, so it'll be 1s2. Then the next 2 go into the 2s orbital, so 1s2, 2s2. And then here for boron, we're actually going to be going into the p orbital. So the next lowest energy orbital is the 2p, and there will be 1 electron in the 2p orbital. So we can label our orbitals in the box diagram: 1s, then 2s, and 2p, and put in our electrons. So there's 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and there's 1 electron in the 2p orbital. And so that'll go in the first box. All of those, and notice in the box diagram that once we get to the 2p orbitals, there are 3 2p orbitals in here. And those 3 2p orbitals are all the same energy, and so the boxes in the box diagram are connected, okay? The next thing, I will do the abbreviated electron configuration for boron. We still have our core electrons are the first shell. So the core electrons are still helium. Okay, remember, the core electrons are always the noble gas electrons from the period above. So it's still helium. Okay, and then we have our 2s2 electrons and 2p1 electrons. In the box diagram, we'll have the abbreviated box diagram. Try that again. We have our helium, and we have our box for the 2s. And when you're doing this, you should always draw in all 3 boxes for the 2p orbitals, even if they're not all filled. Okay, so you go 2 electrons in the 2s, and then 1 electron in the 2p orbital. Okay. And so the next one we go to is carbon. Carbon has 6 electrons, right? 6 protons, so 6 electrons. So the next electron will go into the 2p orbitals also. So this will be 1s2, 2s2, 2p2. And now as we label our orbital, and we start to fill in our orbitals in the box diagram, something we need to think about is, where do those p electrons go? So we're still going to put in our s electrons like we did before until we fill those s orbitals. And now we go to start to fill the p orbitals. And I'll put the first one in, but I've got 2 electrons. So the question is, does this electron go in the same orbital right? The one, and pair up with the first one, or does it go so that it's in the next one? And based on Hund's rule, it says that we're going to start by putting these electrons into separate orbitals so that they're unpaired. We're getting the most unpaired electrons. And the reason for that is there is still a repulsion between electrons. So if you can put electrons in different orbitals, if those orbitals are the same energy, you want to do that first. Okay. And then we can, and so that's going to be the next thing is as we start to fill the p orbitals, the first one goes in the first orbital, then the second one's going to go in the second orbital, and when we get to nitrogen, the third electron will go in the third orbital. So we have 7 electrons, so it'll be 1s2, 2s2, 2p3. So we're grouping together all of those p orbitals here. So we can fit up to 6 electrons in them. So we have our 1s, 2s to label our box diagram, 2p. So we go 1, 2 electrons in each of the first 2s orbitals, and now we have 1, 2, 3 electrons in the p orbitals. And so it's when we get to oxygen, where we have 8 electrons, that we start to see electrons pair up in the p orbitals. So here 1s2, 2s2, 2p4. So the one labeling our orbitals, 1s orbitals, the 2s orbitals still have filled electrons. So the way we put these in here, I'm going to kind of do it the way that I tend to, which is fill each electron or each orbital with 1 electron first. So there's 1, 2, 3, but I have 4 p electrons. So I'm going to go back to the first orbital and put my second electron in there. Okay, next we're going to look at fluorine with 9 total electrons in it. And so this one will be 1s2, 2s2, 2p5. So we have our 1s, the 2s, the 2p orbitals, and we fill in the electrons. 1, 2, 3, 4, 5, 6, 7, 8, and there's our 9th electron there. When we get to neon, now we're going to complete a shell because we're going to get to the next noble gas. Neon has a total of 10 electrons, and so it will be 1s2, 2s2, 2p6. And so we're going to label all of our orbitals, and we are going to insert 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons to make the electron configuration of neon. Now that completes our second period, and so we start the third period with sodium, and sodium has 11 electrons. And so as we do this, now we're going to go with 1s2, 2s2, 2p6. Now we're the next orbital that we're going to fill based on our hierarchy and the energies of those orbitals. Here we have our 1s, 2s, 2p. Now we're on to the 3s orbitals, and after that will be the 3p, 4s, and 3d. So this is our 3s orbital, and there's 1 electron there. So now we have our 1s, 2s, 2p, and 3s orbitals. We have 11 electrons to put in here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and our 11th electron is the one that goes in the 3s orbital. Now, a thing to note here is now we're on to the next period. And so something to really pick out here is the electron configuration of neon, which is a noble gas, is the 1s2, 2s2, 2p6. And so we can represent this in our abbreviated box diagram, or we can represent that piece of it using the brackets and neon, right, to express our noble gas core electron configuration. So here, we now have the neon as our new core. And we have one more electron in to place, which is in the 3s orbital, right? Because our valence shell is the 3s orbitals. Our third shell is our valence shell. And so here we've got neon. And then we have the 3s orbital. And so we can put our electron in like that. Okay, so that's the key, is each time we have a new element in the brackets here, right, it's the element after that we complete that full period of the periodic table that we can start using that for the next period. So we go from sodium to magnesium, which has 12 valence electrons, or excuse me, 12 electrons, 2 valence electrons. And so here it's 1s2, 2s2, 2p6, and 3s2. So 1s, 2s, 2p, and 3s. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay. On to aluminum with 13 valence electrons, 1s2, 2s2, 2p6, 3s2, and now we're on to the 3p orbital, so 3p1. So we've got our 1s, 2s, 2p, 3s, and 3p orbitals now, and we fill it the same way with all 13 electrons in there. All right, and there's our 13th. I'm gonna go try to make that one clearer. 1, 2, okay. And so there's our aluminum. Continuing down this path is silicon. So 14, the 1s2, 2s2, 2p6, 3s2, and 3p2. So we have our 1s, 2s, 2p, 3s, and 3p orbitals. And we've got 14 electrons to fill. 5, 6, 7, 8, 9, 10, 11, 12, 13. And again, this is our second electron to go in the 3p orbitals. And so it's going to be in the next orbital, and it'll be each orbital that has an electron will just be half filled. From silicon to phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. And so on this one, we're going to make sure that each of our p orbitals is half filled for the 3p orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 electrons. And I'm going to skip a couple of these as we proceed. The next one we'll do will be sulfur. And so we'll head up to the, actually I may not, we'll see. The next one we're going to do is sulfur. So sulfur is up here. Ooh, there it goes again. Sulfur is up here, right, which has a total of 16 electrons in it. So it's 1s2, 2s2, 2p6, 3s2, 3p4. Okay. And we're going to put our shells in here, 1s, 2s, 2p, 3s, and 3p. So here, fill it again. And here, now we can start pairing up our p electrons because we have 4 of them. So 1, 2, 3, and 4. You do the same thing with chlorine. Actually, we'll just do that. And maybe do them all. So 17 electrons. So it's 1s2, 2s2, 2p6, 3s2, and 3p5. So 1s, 2s, 2p, 3s, and 3p again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. So there's only one unpaired electron for the chlorine, but when we get to argon, we now have 18 electrons, and we'll pair them all up and complete our next shell. So 1s2, 2s2, 2p6, 3s2, 3p6. So 1s, 2s, 2p, 3s, and 3p orbitals. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There we go. Okay. So that fills up the shell for argon. Now, argon is our next core as we start the third period with potassium. So potassium has 19, that's a 9, really. 19 electrons, so 1s2, 2s2, 2p6, 3s2, 3p6, and now we go to the 4s1. So this is where it's kind of weird. Normally you would think that we'd fill a 3D, but it turns out, based on some subtleties in the energies of the 4s and the 3D, that we actually fill the 4s first. It's slightly lower in energy. And so our orbitals are the 1s, 2s, 2p, 3s, 3d, and 3p, what am I doing? And 4s, and we fill them. Okay, and so there will be 1 electron in the 4s orbital. And since our next core is argon, right? And so argon, we know, accounts for, right, all of the electrons in period above, right? The 1s2, 2s2, 2p6, 3s2, and 3p6. We can abbreviate those, right, in our abbreviated electron configuration. So here we've got now argon 4s1. And so you can see these abbreviated electron configurations are significantly shorter as you get to the larger elements, right? As you go down the periodic table, your core, or writing out your core as the noble gas in brackets makes it a whole heck of a lot easier to write these out quickly. Okay, so our next one is calcium, and then we'll get into our transition metals. Calcium has 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. All right, and then we just fill them up. And so what we'll do now, after this, we have now 2 electrons in the 4s. What we'll do here for the next part, the transition metals, is we're going to write down just abbreviated electron configurations. And what I want you to notice is that for all of these, right, all of the core electrons would be here, right? Those are all going to be filled for every one of these. So I want to focus now on just the last bit, the d electrons that we're going to put in here. So scandium is our first of the transition metals, and there are 21 electrons in it. And so it's going to have an abbreviated electron configuration of argon, 4s2, 3d1. And so all of these are going to be filled, okay? All of those. And so what I'll do for you guys is we're just going to look at how we fill the d electrons for these elements. And I'm going to go and fill out the rest of this table before I post it on Canvas so that you'll have access to this full table. And so I'll do that while you guys are working on the lab today and then post it. So I want you to see how the d electrons fill for these transition metals, knowing that all of these orbitals there are going to be filled. So this is going to be our 3d set of orbitals. And so for scandium, there's only 1. When we look at titanium, we've got 22 electrons. And so we have argon, 4s2, 3d2. And so here, again, our 3ds, we've got 1, 2 electrons in the d orbitals because we fill one orbital at a time. When we go to vanadium, we now have 23. And so with vanadium, it's argon, 4s2, 3d3. And so now we've got all of them filled, and now we have 1, 2, 3 electrons in the d orbitals. But I want to sort of make a note right here that there's going to be something a little bit funky about chromium. So for chromium, we've got a total of 24 electrons. And what winds up happening is because of how the energies of the orbitals when they're filled versus not filled, there's some subtleties that happen. And so there's an exception to this filling when it comes to chromium. So we have argon. What it'll be is 4s1, 3d5. There's just an inherent stability to having our 1 electron in the 4s and 5 electrons, basically a set of d orbitals that are completely half filled. Okay, so this is going to be an exception to the rule, the chromium here. We'll have 1 electron in all of these orbitals. Okay, and so I note that that's part of the reason I wanted to get to this, is that there is an exception there. And this is important for something we'll talk about a little bit later. The number of unpaired electrons has a lot to do with the magnetic properties of a substance. And so we'll talk about that a little bit later in the term, but you need to know how those are filled for that exception. And then when we go from chromium to manganese, 25 electrons, again, we're going to have that filled 4s orbital. It'll be 4s2, 3d5. Okay, and so here, you're going to have now the s orbitals filled. Oh, I did it on the wrong one. 4s there. 1, 2, 3d, 1, 2, 3, 4, 5. And so I'm going to actually skip to the last the last one we're going to do right now. I'm going to skip it, and you can basically fill these the rest of the way, right? For our next one is iron. Iron would be argon, 4s2, 3d6, right? To cobalt, which would be argon, 4s2, 3d7. The one that I want to get to is way down here, number 29 is copper, because that's our other exception. And then you'll see as I fill in the table and post it later, you can sort of check these electron configurations, but copper is our other exception. So on copper, you now have 29 electrons, right? And you're going to have, so your 4s and 3ds are going to have the exception in there. So here, of argon, 4s1. So the s orbital will remain half filled, and you'll fill completely the 3d orbital, so 3d10. And so you'll have one electron in there, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, this has to do with the subtleties of the energies of those orbitals as you're filling them. And so what I'll do is we're gonna end here. We'll finish up chapter 7 on Monday and start in on chapter 8 as we look at periodic trends on Monday, and then we jump into some bonding. What I'll do is I'll fill out the rest of this table while you guys are working today, and I'll post this along with the other slides so that you have some slides to look at. And so I'm going to end our recording right there, because really all we did today is do some more filling of orbitals for the electron configurations, and you guys can start your lab.